Before Max Planck entered the scientific stage, physics was widely considered a nearly complete and perfected discipline. By the late 19th century, many leading scientists believed that the fundamental laws governing nature had already been discovered. Classical physics, built on the foundations laid by Isaac Newton, James Clerk Maxwell, and Rudolf Clausius, appeared to explain almost every observable phenomenon. Motion, heat, light, electricity, and magnetism were all described through elegant equations that seemed universal and timeless. The universe, according to this worldview, functioned like a precise mechanical clock, predictable and orderly, governed by continuous laws that left little room for uncertainty or surprise. Newtonian mechanics dominated the understanding of motion and forces. It successfully explained the movement of planets, the fall of objects, and the behavior of machines. Maxwell's equations unified electricity, magnetism, and light into a single theoretical framework, revealing that light itself was an electromagnetic wave traveling smoothly through space. Thermodynamics described heat and energy with impressive accuracy, introducing concepts such as entropy and energy conservation. Together, these theories formed a powerful and coherent picture of reality, one in which nature behaved continuously and deterministically. This confidence was so strong that some physicists believed future research would only refine measurements, not uncover new principles. There was a sense that physics had reached its golden age, and that the remaining work involved filling small gaps in existing theories. The idea that a radical transformation was imminent seemed almost unthinkable. Yet beneath this surface of certainty, cracks were beginning to form, subtle at first, but increasingly impossible to ignore. One of the earliest warning signs came from studies of heat and radiation. Scientists were trying to understand how objects emit energy when heated, particularly how the color and intensity of radiation change with temperature. Everyday experiences, such as metal glowing red or white when heated, hinted at complex processes that classical physics struggled to explain fully. Experiments showed clear patterns, but theoretical predictions did not always match observed results. The most troubling issue emerged from research into blackbody radiation. A blackbody is an idealized object that absorbs all incoming radiation and emits energy solely based on its temperature. Physicists measured the spectrum of radiation emitted by such objects and found precise experimental curves that described how energy was distributed across different frequencies. Classical theories attempted to reproduce these curves using well-established principles, but they failed dramatically at high frequencies. According to classical physics, energy should be emitted continuously, and higher frequencies should carry increasingly large amounts of energy. This prediction led to what became known as the ultraviolet catastrophe. The equations suggested that a hot object should emit infinite energy at short wavelengths, an outcome that was physically impossible and contradicted every experimental observation. Instead of diverging to infinity, real radiation curves peaked at certain frequencies and then declined smoothly. This contradiction was not a minor technical flaw. It struck at the heart of classical physics. If the existing laws could not correctly describe something as fundamental as heat radiation, then their supposed universality was called into question. Scientists attempted various fixes, modifying equations and introducing assumptions, but none provided a satisfactory explanation. The problem lingered, unresolved and unsettling. At the same time, other experimental results hinted that classical ideas might be incomplete. Studies of atomic spectra revealed that atoms emitted light at specific, discrete wavelengths rather than across a continuous range. Classical models of atoms, which imagined electrons orbiting the nucleus like planets around the Sun, could not explain why only certain frequencies appeared. According to classical electrodynamics, accelerating charges should continuously radiate energy and spiral into the nucleus, making stable atoms impossible. Yet atoms were clearly stable, and matter did not collapse. These inconsistencies created a growing sense of unease among physicists. While many still believed that classical theory would ultimately prevail, others recognized that deeper changes might be necessary. The crisis was not immediately obvious to the public, but within scientific circles, debates intensified. Conferences and journals filled with discussions about unresolved anomalies, and younger scientists began questioning long-held assumptions. Despite these warning signs, resistance to radical change remained strong. Classical physics had earned its authority through centuries of success, and abandoning its principles seemed risky and unnecessary to many. The prevailing belief was that nature behaved smoothly and continuously, and that any apparent discontinuities were artifacts of incomplete knowledge or experimental error. Few were willing to suggest that continuity itself might be an illusion. This intellectual environment shaped the mindset of physicists at the turn of the century, including Max Planck. He was trained deeply in classical thermodynamics and initially shared the belief that existing laws described reality accurately. Planck was not a revolutionary by temperament. He valued order, tradition, and mathematical rigor. Ironically, it was precisely this devotion to classical principles that led him to confront their limitations so directly. As experimental evidence continued to accumulate, the pressure on classical physics grew. The Blackbody radiation problem stood as a symbol of this crisis, a clear and undeniable failure that demanded explanation. Laboratories across Europe produced increasingly accurate data, leaving no room for dismissing the discrepancy as experimental error. Theory had to adapt, or it would collapse under the weight of its own contradictions. This period before Planck's breakthrough represents a pivotal moment in scientific history. It was a time when confidence coexisted with uncertainty, when success masked fragility, and when the foundations of physics were quietly eroding. The crisis of classical physics was not a sudden collapse, but a slow unraveling, driven by experiments that refused to conform to established ideas. In retrospect, this era appears as the calm before a storm. The laws that once seemed eternal were about to be challenged in ways no one could have predicted. The stage was set for a profound transformation, one that would replace certainty with probability and continuity with discreteness. Before Max Planck introduced his revolutionary idea, physics stood at the edge of a new frontier, unaware that the universe it thought it understood was far stranger and more complex than imagined. As the 19th century drew to a close, the growing tension within physics became impossible to hide. What once appeared to be a solid and complete structure now showed signs of strain under the weight of unexplained phenomena. The confidence that had defined classical physics slowly transformed into cautious doubt. This was not a dramatic collapse, but a gradual realization that the universe was refusing to obey the rules scientists believed were final. The crisis deepened as more precise experiments exposed the limits of traditional theories. One of the strongest pillars of classical physics was the belief in continuity. Energy, matter, space, and time were all assumed to vary smoothly, without jumps or breaks. This assumption was so deeply rooted that few questioned it openly. Every equation of mechanics, electromagnetism, and thermodynamics relied on this idea. Yet experiments were beginning to suggest that nature might not be as smooth as once believed. Radiation experiments became increasingly accurate thanks to advances in laboratory technology. New instruments allowed physicists to measure wavelengths and intensities with unprecedented precision. What they saw was consistent and repeatable, but deeply troubling. No matter how carefully classical equations were adjusted, they refused to match reality. The mismatch was not small, it was fundamental. Theoretical curves diverged wildly from experimental ones, especially at high frequencies, revealing a failure that could not be ignored. Attempts to save classical physics multiplied. Some scientists proposed that matter had unknown properties that would eventually explain the discrepancy. Others suggested that experimental limitations were responsible. Still, others believed that a missing variable or correction factor could restore harmony. These efforts reflected a strong emotional and intellectual attachment to existing laws. Classical physics was not just a theory, it was a world that had shaped scientific thinking for generations. Meanwhile, the atomic world was becoming increasingly mysterious. Spectroscopy revealed that each element emitted light at its own unique set of frequencies, like a fingerprint. These sharp spectral lines contradicted the idea of continuous emission. Classical models could not explain why atoms behaved this way, nor why they remained stable over time. The deeper physicists looked into matter, the less classical explanations seemed to apply. The problem extended beyond radiation and atoms. Heat capacity measurements of solids showed unexpected behavior at low temperatures. Classical theory predicted that heat capacity should remain constant, but experiments showed that it decreased dramatically as temperature dropped. Once again, theory and reality diverged. These anomalies accumulated like cracks in a dam, each one weakening the structure. Despite these issues, the scientific community remained divided. Some researchers sensed that a revolutionary change was approaching, while others insisted that the problems were temporary. Textbooks still presented classical physics as complete, and university education reinforced traditional methods. Students were trained to solve equations, not to question assumptions. This created a strange duality in physics, outward confidence paired with inner uncertainty. Philosophically, the implications were unsettling. Classical physics supported a deterministic universe, where the future could be predicted precisely if all forces and positions were known. This idea aligned well with Enlightenment thinking and the belief in rational order. If classical laws were incomplete, then determinism itself might be at risk. Such a possibility was deeply uncomfortable, not just scientifically, but culturally. Max Planck lived and worked within this atmosphere of contradiction. He was aware of the growing problems, yet he remained committed to classical ideas longer than many of his contemporaries. For him, the laws of thermodynamics represented absolute truths. He believed that entropy and energy conservation reflected deep principles of nature that could not be violated. This belief guided his approach to unresolved problems. What made the crisis so significant was that it could not be solved by incremental improvement. Classical physics had reached the limits of its explanatory power. The anomalies were not at the edges of knowledge. They were embedded in fundamental phenomena like heat, light, and matter. Each failed explanation made it clearer that something essential was missing. Scientific journals of the time reveal the growing frustration. Papers often ended with unresolved questions, and conferences featured heated debates. Experimentalists insisted that their data was correct, while theorists struggled to adapt their equations. The harmony between theory and experiment, once a defining strength of physics, was breaking down. This breakdown marked a turning point in the history of science. For centuries, progress had followed a pattern of refinement and expansion. Now, that pattern no longer worked. The existing framework could not simply be extended, it had to be reconsidered. This realization did not arrive all at once, but its impact was profound. The crisis of classical physics also revealed the human side of science. Pride, tradition, and fear of uncertainty played powerful roles. Many physicists had built their careers on classical theories, and abandoning them felt like undermining their life's work. Younger scientists, less invested in the old framework, were more open to radical ideas, creating a generational divide. As experimental evidence continued to defy expectations, the need for a new approach became unavoidable. Nature was signaling that its rules were different from what humans had assumed. The universe was not obligated to conform to elegant equations or philosophical preferences. It simply behaved as it did, and it was the task of science to understand it honestly. This moment in history represents the threshold between two eras. On one side stood classical physics, powerful yet limited, confident yet fragile. On the other side lay an unknown territory that would later be called the quantum world. Before Max Planck introduced his revolutionary concept, physics was suspended between these two realms, aware of its problems but uncertain of the solution. The crisis before Planck was not a failure of intelligence or effort. It was a natural stage in the evolution of knowledge. Every scientific framework eventually encounters questions it cannot answer. What made this crisis unique was its depth and its consequences. It forced physicists to reconsider their most basic assumptions about reality. In hindsight, the signs were clear. Discrete spectra, unstable equations, and experimental contradictions all pointed toward a deeper truth. But at the time, the path forward was hidden. The scientific community stood at the edge of a transformation it could not yet imagine. Classical physics had reached its limits, and the universe was preparing to reveal a new and astonishing order, one that would forever change humanity's understanding of nature. The problem that would eventually reshape modern physics began quietly, inside laboratories filled with furnaces, glowing cavities, and carefully calibrated instruments. Scientists were trying to understand a simple but fundamental question: how does an object emit energy when it is heated? At first glance, the question seemed ordinary, almost trivial. People had observed glowing hot metal, burning coal, and radiant flames for centuries. Yet, when physicists attempted to describe this process with mathematical precision, they encountered one of the most serious failures in the history of classical science. To study thermal radiation in a controlled way, physicists introduced the concept of a blackbody. A blackbody was defined as an ideal object that absorbs all incoming radiation and reflects none. Because it absorbs everything, the radiation it emits depends only on its temperature, not on its shape or material. In practice, scientists approximated a blackbody using a hollow cavity with a small hole. Radiation entering the hole would bounce around inside and be almost completely absorbed, while radiation escaping the hole would closely match that of a perfect blackbody. When such a cavity was heated, it emitted radiation with a very specific pattern. Experiments showed that the intensity of radiation varied with frequency and temperature in a predictable way. At low frequencies, the intensity increased gradually. At higher frequencies, it reached a peak and then declined sharply. This smooth curve appeared consistently in experiments across different laboratories and countries. The data was reliable, precise, and impossible to dismiss. Classical physics now faced a test. Using established laws of thermodynamics and electromagnetism, physicists attempted to derive a formula that would match the observed radiation curve. Early successes seemed promising. Wilhelm Wien proposed a law that accurately described the high-frequency part of the spectrum, while Lord Rayleigh and James Jeans developed a formula that worked well at low frequencies. However, neither approach could explain the full range of observations. The Rayleigh-Jeans law, derived directly from classical assumptions, led to a shocking result. According to this formula, the intensity of radiation should increase indefinitely as frequency increased. At very high frequencies, the predicted energy output approached infinity. This result implied that a heated object should release an infinite amount of energy, which was clearly impossible. This absurd prediction became known as the Ultraviolet Catastrophe. The Ultraviolet Catastrophe was more than just an incorrect calculation. It represented a complete breakdown of classical reasoning. The equations were mathematically sound, derived from principles that had been trusted for decades. Yet they produced a result that violated common sense, experimental evidence, and the conservation of energy. Something was fundamentally wrong, but no one could see where. Physicists attempted to explain away the problem. Some argued that the classical laws might not apply at very high frequencies, though no clear reason was given. Others suggested that matter might interact with radiation in unknown ways that suppressed high-frequency emissions. These ideas, however, lacked solid theoretical foundations and failed to provide predictive power. What made the problem especially disturbing was that it involved everyday physics. Thermal radiation was not an exotic phenomenon observed only in extreme conditions. It occurred whenever an object was heated, from a glowing stove to the surface of the sun. If classical physics could not explain such a common process, its claim to universality was severely weakened. The Blackbody radiation problem also highlighted the limits of classical statistical mechanics. According to classical theory, energy should be distributed equally among all possible modes of vibration, a principle known as equipartition of energy. This assumption worked well for many systems, but failed catastrophically when applied to radiation. The infinite number of possible electromagnetic modes led directly to infinite energy, exposing a fatal flaw in the theory. Experimentalists continued refining their measurements, hoping that improved accuracy might resolve the discrepancy. Instead, better data only confirmed the problem. The radiation curves became sharper and more precise, leaving no room for classical predictions to hide. The mismatch between theory and experiment was undeniable. By the late 19th century, the Blackbody radiation problem had become a central issue in physics. It was discussed widely in scientific journals and conferences. Leading physicists were aware that a solution was needed, but no one knew how to find it without abandoning deeply held assumptions. The problem was not just technical, it was conceptual. It challenged the idea that energy could vary continuously, a cornerstone of classical thought. This crisis placed physics in an uncomfortable position. On the surface, the discipline appeared strong and mature. Beneath that surface, it was struggling with a problem it could not solve. The Blackbody radiation problem became a symbol of this hidden instability, a warning that the foundations of physics were not as secure as they seemed. Max Planck entered this scene as a theoretical physicist with a strong background in thermodynamics. He was deeply interested in the nature of entropy and the second law of thermodynamics, which he regarded as absolute truths. Unlike some of his contemporaries, Planck was not motivated by experimental curiosity alone. He sought a theoretical explanation that preserved order and consistency. Planck initially attempted to derive the Blackbody radiation formula using classical methods. Like others before him, he failed. The equations stubbornly refused to produce the observed curve. Faced with this impasse, Planck made a decision that he later described as an act of desperation. He introduced a mathematical assumption that energy could only be emitted or absorbed in discrete amounts proportional to frequency. At first, Planck did not view this assumption as a statement about physical reality. To him, it was a formal trick, a way to make the mathematics work. Yet this single step resolved the Blackbody radiation problem completely. His formula matched experimental data across all frequencies with remarkable accuracy. The ultraviolet catastrophe vanished. Although the full implications of Planck's solution would unfold later, the Blackbody radiation problem was the doorway through which quantum theory entered physics. It exposed the failure of classical ideas and forced scientists to consider a radically different view of energy and matter. What began as a technical issue in thermal radiation became the catalyst for a revolution. The importance of the Blackbody radiation problem lies not only in its solution, but in what it revealed about science itself. It showed that even the most successful theories have limits. It demonstrated the power of experiment to challenge established beliefs. Most importantly, it revealed that nature does not conform to human expectations of simplicity or continuity. Before its resolution, physics stood at a crossroads. One path clung to classical certainty, despite mounting evidence of failure. The other path required embracing a strange and unfamiliar idea, one that would eventually transform science and technology. The Blackbody radiation problem forced physicists to choose, marking the beginning of a new era. This problem, once seen as a narrow technical issue, became one of the most important questions ever asked in physics. It exposed the cracks in classical theory and illuminated the path toward quantum mechanics. Without it, the quantum revolution might have been delayed by decades. Through the glow of heated cavities and the silence of failed equations, the universe signaled that it was ready to reveal a deeper truth. As the struggle to understand Blackbody radiation continued, the scientific community slowly realized that the problem was not confined to a single equation or experimental setup. It reflected a deeper conflict between observation and assumption. Classical physics relied on the idea that matter and energy behaved in smooth, continuous ways, but the radiation curves stubbornly suggested otherwise. Each attempt to force experimental results into classical formulas only highlighted the inadequacy of the existing framework. The ultraviolet catastrophe became a powerful symbol of this failure. It was not merely an embarrassing mathematical error, but a direct contradiction of physical reality. If classical theory were correct, every heated object would emit infinite energy, and the universe would be unstable. The fact that the world clearly did not behave this way meant that the underlying assumptions had to be questioned. For many physicists, this realization was deeply unsettling. Theoretical debates intensified as the implications became clearer. Some researchers tried to limit the applicability of classical physics, suggesting that its laws might only work under certain conditions. Others speculated about unknown interactions between matter and radiation that could suppress high-frequency emissions. These ideas, however, lacked experimental support and failed to provide a coherent explanation. The more the problem was examined, the more it resisted classical solutions. At the same time, the Blackbody radiation problem revealed the limits of analogy-based reasoning Classical physicists often treated electromagnetic radiation as a collection of waves, similar to sound or water waves. While this analogy worked well at low frequencies, it broke down completely at high frequencies. The assumption that all modes of vibration should carry equal energy no longer made sense when confronted with experimental data. This realization marked a shift in scientific thinking. Physicists began to accept that intuition built from everyday experience might not apply at microscopic scales. The smooth, continuous world perceived by human senses was not necessarily the true nature of reality. The Blackbody radiation problem forced scientists to confront the possibility that nature operated according to unfamiliar rules. Max Planck's role in this unfolding crisis was unique. He was driven not by a desire to overthrow classical physics, but by a determination to preserve the laws of thermodynamics. Planck believed that entropy was a fundamental principle, valid without exception. When classical methods failed to explain Blackbody radiation, he searched for a new approach that would still respect thermodynamic laws. By introducing the idea that energy exchange occurred in discrete units, Planck resolved the contradiction without fully embracing its philosophical consequences. His formula fit the experimental data perfectly, providing a single expression that worked across all frequencies and temperatures. What had seemed impossible suddenly became clear, and the ultraviolet catastrophe disappeared as if it had never existed. The scientific community initially viewed Planck's solution with cautious interest rather than excitement. Many physicists saw the quantization of energy as a convenient mathematical trick, rather than a description of reality. Even Planck himself hesitated to interpret it physically. He believed that future developments might restore continuity at a deeper level. Despite this hesitation, the success of Planck's formula could not be ignored. It demonstrated that classical assumptions about energy distribution were incorrect. The Blackbody radiation problem had been solved, but at the cost of introducing a concept that challenged centuries of scientific thought. The solution worked precisely because it broke with tradition. As researchers began applying Planck's idea to other problems, its significance became undeniable. Einstein's explanation of the photoelectric effect, which treated light as composed of energy quanta, built directly on Planck's work. These developments confirmed that quantization was not limited to Blackbody radiation, but was a fundamental feature of nature. Looking back, the Blackbody radiation problem stands as a turning point in the history of science. It was the moment when classical physics reached its limits and a new framework began to emerge. The problem forced physicists to abandon the comforting belief that the universe was entirely continuous and predictable. In its place arose a world governed by probabilities, discrete interactions, and surprising behavior. The resolution of the Blackbody radiation problem also changed the relationship between theory and experiment. It showed that experimental results must guide theoretical development, even when they contradict deeply held beliefs. Mathematics alone was not enough. It had to reflect physical reality. This lesson became a guiding principle of modern physics. Beyond its scientific impact, the Blackbody radiation problem revealed something profound about human understanding. It showed that knowledge progresses through crisis and uncertainty. Breakthroughs often arise not from confidence, but from failure. When established ideas collapse, new possibilities emerge. In the end, the Blackbody radiation problem was not just about heated objects and glowing cavities. It was about the limits of human assumptions and the willingness to revise them. It marked the point where physics stepped into the quantum age, guided by experimental truth rather than philosophical comfort. Through this problem, science learned that the universe is not obligated to align with human intuition. It operates according to its own rules, waiting to be discovered. The Blackbody radiation problem forced physicists to listen more closely to nature, and in doing so, it opened the door to one of the greatest revolutions in scientific history. The third keynote centers on one of the most radical ideas ever introduced in science: the concept that energy is not exchanged continuously, but in discrete packets. This idea, known as the introduction of energy quanta, emerged from Max Planck's attempt to solve the Blackbody radiation problem and quietly overturned centuries of classical thinking. Before Planck, energy was understood as a smooth, flowing quantity. Whether describing heat, light, or motion, classical physics assumed that energy could increase or decrease by any amount, no matter how small. This assumption worked well for large-scale phenomena and matched everyday experience. A dimmer switch, for example, appears to change light brightness smoothly, reinforcing the belief in continuity. No one suspected that, at a deeper level, energy might behave differently. While studying thermal radiation, Planck found that classical equations could not reproduce experimental results. In a moment of intellectual desperation, he made an extraordinary assumption. The atoms in the walls of a heated cavity could only emit or absorb energy in fixed amounts. These amounts were proportional to the frequency of radiation, meaning higher frequency radiation carried larger packets of energy. Planck expressed this relationship through a new constant, now called Planck's constant, which set the scale of these energy units. This assumption was not based on experimental proof at the time. It was a mathematical strategy designed to make the theory fit the data. Yet it worked perfectly. Planck's formula matched the observed radiation spectrum across all frequencies, eliminating the ultraviolet catastrophe and restoring agreement between theory and experiment. Despite its success, the idea of energy quanta was deeply unsettling. It suggested that nature operates in jumps rather than smooth transitions. This contradicted the core principles of classical mechanics and electromagnetism. Planck himself was uncomfortable with the implications and initially believed that energy quantization might be a property of matter interacting with radiation, not of radiation itself. The true significance of energy quanta became clearer when Albert Einstein applied the concept to explain the photoelectric effect. Einstein proposed that light itself consists of discrete packets of energy, later called photons. This bold interpretation transformed Planck's mathematical assumption into a physical reality. Experiments soon confirmed Einstein's predictions, providing strong evidence that quantization was fundamental. The introduction of energy quanta reshaped the understanding of atomic behavior. It explained why atoms emit light at specific frequencies and why electrons occupy stable energy levels. These insights laid the groundwork for quantum mechanics, a new framework that replaced certainty with probability and classical paths with wave functions. Beyond theory, the impact of energy quanta extended into technology. Modern devices such as lasers, solar cells, and semiconductors all rely on quantum principles. What began as a theoretical fix to a radiation problem became the foundation of the digital age. In essence, the introduction of energy quanta marked a turning point in science. It revealed that reality at its most fundamental level is not continuous but quantized. This single idea challenged intuition, reshaped physics, and opened a new window into the nature of the universe. The fourth keynote focuses on a decisive moment in scientific history, the birth of quantum theory in the year 1900. This moment did not arrive with dramatic declarations or immediate celebration. Instead, it emerged quietly from Max Planck's effort to solve a specific technical problem. Yet its consequences would transform physics more profoundly than almost any discovery before or since. On December 14, 1900, Max Planck presented a paper to the German Physical Society in Berlin. In it, he introduced a formula that accurately described blackbody radiation across all frequencies. What made this formula revolutionary was the assumption behind it. Energy could only be emitted or absorbed in discrete units. Although Planck viewed this assumption as a mathematical convenience, history would recognize it as the first statement of quantum theory. At the time, the scientific world did not immediately grasp the importance of this idea. Planck himself remained cautious. He believed that the quantization of energy might eventually be explained within classical physics. For him, the continuity of nature was still a deeply held belief. Nevertheless, the success of his radiation law could not be denied, and it quickly gained acceptance as the correct description of experimental data. The year 1900 is now remembered as the dividing line between classical and modern physics. Before this moment, physical laws were built on certainty, continuity, and determinism. After it, physics slowly began to accept discreteness, uncertainty, and probability. The transition was gradual, but the seed had been planted. Quantum theory did not emerge fully formed. Planck's work opened a door rather than providing a complete framework. In the years that followed, other physicists stepped through that door and expanded the idea in unexpected ways. Albert Einstein extended Planck's concept by proposing that light itself is quantized. Niels Bohr applied quantization to atomic structure, explaining why atoms emit discrete spectral lines. Each development confirmed that Planck's idea was not a mathematical trick, but a fundamental feature of nature. The birth of quantum theory also marked a shift in how science approached reality. Classical physics had offered a comforting vision of a predictable universe. Quantum theory challenged this view, suggesting that at the microscopic level, outcomes could only be described in terms of probabilities. This was not merely a scientific adjustment, but a philosophical shock. The universe was no longer fully knowable in the classical sense. Resistance to quantum theory was strong. Many leading physicists, including Planck himself, struggled to accept its implications. The idea that energy and later matter behaved in discrete steps seemed to undermine the elegance of classical laws. Yet experiment after experiment supported the new theory. Over time, evidence outweighed discomfort. The significance of 1900 lies not just in a single equation, but in a change of perspective. Quantum theory introduced a new way of thinking about nature, one that embraced limits, uncertainty, and hidden structure. It acknowledged that human intuition, shaped by the macroscopic world, was not a reliable guide at atomic scales. Today, quantum theory underpins much of modern science and technology. From transistors and lasers to medical imaging and quantum computing, its applications are everywhere. None of this would have been possible without the quiet revolution that began in 1900. The birth of quantum theory reminds us that great scientific changes often begin modestly. A single idea, introduced to solve a narrow problem, can reshape the entire understanding of reality. Max Planck's contribution did exactly that, marking the beginning of a new era in science and forever altering humanity's view of the universe. The fifth keynote explores the resistance and criticism that followed the introduction of quantum ideas. revealing how revolutionary concepts often face skepticism before gaining acceptance. When Max Planck introduced the idea of energy quanta, it did not immediately inspire enthusiasm. Instead, it challenged deeply rooted beliefs that had guided physics for centuries, and many scientists were unwilling to abandon those foundations so easily. At the turn of the 20th century, classical physics was not just a collection of theories. It was a proven framework that had delivered extraordinary success. It explained planetary motion, engineering principles, electricity, magnetism, and thermodynamics with remarkable accuracy. For many physicists, questioning its assumptions felt unnecessary and even irresponsible. The notion that energy behaved in discrete units seemed to contradict both mathematical elegance and everyday experience. One major source of resistance came from the principle of continuity. Classical physics assumed that physical quantities changed smoothly, without abrupt jumps. Planck's idea suggested the opposite, that energy could be exchanged only in fixed amounts. To many scientists, this appeared artificial and unphysical. They viewed quantization as a mathematical trick rather than a real feature of nature. Even Max Planck himself hesitated to fully embrace the implications of his discovery. He believed strongly in classical thermodynamics and hoped that quantization would eventually be explained in classical terms. This hesitation influenced how his work was initially received. If the originator of the idea treated it cautiously, others felt justified in doing the same. Prominent physicists expressed open skepticism. Some argued that quantization violated fundamental laws of electromagnetism. Others believed that unknown mechanisms within matter would restore continuity once better models were developed. These critics were not dismissive out of ignorance, but out of commitment to a framework that had served science well. Another challenge came from the lack of immediate experimental confirmation beyond Blackbody radiation. While Planck's formula fit the data perfectly, there was little direct evidence that energy itself was quantized. Without broader experimental support, many physicists remained unconvinced. They preferred to wait for alternative explanations that preserved classical ideas. The turning point came gradually, as quantum concepts proved useful in solving other problems. Albert Einstein's explanation of the photoelectric effect provided strong evidence that light behaved in discrete packets. Later, Niels Bohr's atomic model explained spectral lines that classical theory could not. Each success weakened resistance and strengthened the case for quantum theory. Despite growing evidence, acceptance was slow and often uncomfortable. Quantum mechanics challenged not only physical laws, but also philosophical assumptions about causality and determinism. The idea that outcomes could only be predicted probabilistically disturbed many scientists. Debates over interpretation continued for decades and, in some cases, still persist today. The resistance to quantum theory highlights an important aspect of scientific progress. New ideas are not accepted solely because they are correct. They must also overcome tradition, intuition, and professional investment. Scientists are human, influenced by habits of thought and emotional attachment to familiar theories. In retrospect, the criticism faced by quantum theory was a necessary part of its development. Rigorous skepticism forced proponents to refine their arguments and produce stronger experimental evidence. Through this process, quantum theory emerged not as a speculative idea, but as a robust and reliable framework. The story of resistance to quantum ideas reminds us that scientific revolutions are rarely smooth. They involve doubt, debate, and sometimes discomfort. Yet it is through this struggle that knowledge advances. What was once controversial becomes foundational, and what was once resisted becomes indispensable to understanding the universe. The sixth keynote highlights the profound influence Max Planck's ideas had on other great minds, and how those ideas shaped the development of modern physics. Although Planck himself introduced energy quantization cautiously, his work became the foundation upon which a new generation of physicists built an entirely new understanding of nature. The ripple effects of his discovery reached far beyond Blackbody radiation and transformed the scientific landscape. Albert Einstein was among the first to recognize the deeper meaning of Planck's work. In 1905, Einstein applied the concept of energy quanta to explain the photoelectric effect, a phenomenon in which light striking a metal surface ejects electrons. Classical wave theory could not explain why light below a certain frequency failed to release electrons, regardless of its intensity. Einstein proposed that light consisted of discrete packets of energy, later called photons, and that only photons with sufficient energy could free electrons. This explanation not only solved the problem, but also provided strong evidence that quantization was a real physical property of light, not just a mathematical convenience. Einstein's work extended Planck's idea into a new domain and demonstrated its explanatory power. It marked a turning point in the acceptance of quantum concepts and earned Einstein the Nobel Prize in Physics. More importantly, it confirmed that Planck's constant played a fundamental role in nature. Another major figure influenced by Planck was Niels Bohr. In 1913, Bohr developed a model of the atom that incorporated quantized energy levels. He proposed that electrons could occupy only specific orbits around the nucleus, and that they emitted or absorbed energy only when jumping between these orbits. This model successfully explained the discrete spectral lines observed in atomic emission, a long-standing mystery in physics. Bohr's work showed that quantization governed the structure of matter itself. As quantum ideas spread, they inspired a wave of innovation among physicists. Louis de Broglie suggested that particles such as electrons exhibit wave-like behavior, extending quantum principles to matter. Werner Heisenberg introduced matrix mechanics, while Erwin Schrödinger developed wave mechanics. Together, these approaches formed the mathematical framework of quantum mechanics, a theory far more comprehensive than Planck's original proposal. Planck's influence was not limited to individual discoveries. His work changed how physicists approached problems. It encouraged them to question assumptions, accept counterintuitive results, and rely on experimental evidence over intuition. The classical picture of a predictable universe gave way to a probabilistic one, where uncertainty was an inherent feature of nature. The collaborative nature of this transformation is significant. Quantum theory did not emerge from a single mind, but from a network of thinkers responding to the challenge Planck's idea presented. Each contribution built upon the last, demonstrating the cumulative power of scientific inquiry. The impact of this intellectual revolution extended beyond theory. Quantum principles enabled the development of technologies that define the modern world, from transistors and lasers to medical imaging and communication systems. These advancements trace their origins back to Planck's initial insight. In essence, Max Planck's greatest legacy lies in the minds he inspired. His willingness to challenge classical assumptions opened the door for others to explore a new realm of physics. Through the work of Einstein, Bohr, and many others, Planck's idea evolved into a comprehensive theory that reshaped science and technology, proving that even the most cautious breakthrough can ignite a revolution. The seventh keynote focuses on the long-term impact of Max Planck's discovery and how it permanently reshaped science, technology, and humanity's understanding of the universe. What began as a solution to a narrow problem in thermal radiation evolved into a foundation upon which much of modern civilization now rests. The true significance of Planck's work is best understood not in the moment of its discovery, but in the century of progress that followed. One of the most profound impacts of Planck's contribution was the complete transformation of physics. Quantum theory replaced classical certainty with a new framework based on probabilities and discrete interactions. This shift changed how scientists understood matter, energy, space, and time. At microscopic scales, particles no longer followed predictable paths. Instead, their behavior could only be described statistically. This new view challenged intuition, but provided unmatched accuracy in describing nature. The influence of quantum theory extended rapidly into other scientific fields. In chemistry, it explained the structure of atoms, the formation of chemical bonds, and the behavior of molecules. Without quantum mechanics, modern chemistry would lack its theoretical foundation. In materials science, quantum principles clarified why materials conduct electricity, act as insulators, or behave as semiconductors. These insights enabled the design of new materials with tailored properties. Technology represents one of the most visible long-term effects of Planck's legacy. The invention of the transistor, the basic building block of all modern electronics, relies entirely on quantum behavior in semiconductors. Computers, smartphones, and the Internet itself exist because of quantum mechanics. Lasers, another quantum-based technology, are essential in medicine, communication, manufacturing, and entertainment. Medical science has also benefited enormously. Techniques such as magnetic resonance imaging and radiation therapy depend on quantum interactions at the atomic level. These technologies have saved countless lives and transformed healthcare, demonstrating how abstract theoretical ideas can lead to practical and humanitarian outcomes. Beyond applications, quantum theory altered the philosophy of science. It revealed that human intuition, shaped by everyday experience, is not a reliable guide to fundamental reality. Concepts like uncertainty, wave, particle duality, and superposition challenged traditional ideas of causality and determinism. This philosophical shift influenced not only physicists, but also thinkers in philosophy and even art and literature. The long-term impact of Planck's work continues into the present. Emerging fields such as quantum computing and quantum communication promise to revolutionize data processing and security. These technologies exploit quantum superposition and entanglement, concepts that trace their origins back to Planck's constant. Although still in development, they represent the next stage of the quantum revolution. Planck's legacy also offers a lesson about scientific progress. His discovery shows that transformative ideas often arise from attempts to solve specific problems, not from a desire to overturn established beliefs. It highlights the importance of intellectual honesty and openness to unexpected results. Progress sometimes requires accepting ideas that seem strange or uncomfortable at first. In the broader context of human knowledge, Max Planck's contribution ranks among the most influential in history. By introducing the concept of quantization, he revealed a hidden structure of reality that had been invisible to classical physics. His work reminds us that the universe is deeper and more complex than it appears, and that understanding it requires humility and curiosity. Ultimately, the long-term impact of Planck's discovery lies in how it changed humanity's relationship with nature. It transformed mystery into knowledge, confusion into insight, and abstract theory into world-changing technology. More than a century later, the quantum leap Max Planck initiated continues to shape the future of science and society.